My name is Artur. I'm a member of Czajka. By day, I work at Artur Technologies. By night, I tinker with Haskell. And today, my starting point is this book. I will assume that most of you at least heard about it. And I want to show you how concepts coming from functional programming align with the contents of this book. So first off is immutability. Immutability is the concept that anyone that did something with concurrency already had to embrace for at least part of the application to avoid chaos. The difference in the functional thinking is that the immutability is the default, and you only use mutable state as a means for optimization. And there are, of course, already widely used examples of such systems that use immutable data structures. For example, you're probably familiar with Git. Each commit stored in Git is immutable, and new commit is built upon the old commits. So if all the ingredients of my current state are immutable, my current structure is also immutable. But it represents an ever-changing being, which is the code that we write. However, if you don't consider your code base dynamic enough, I refer you to the keynote John Carmack gave at QuakeCon 2013, where he said that, well, he wanted to learn Haskell. In order to do that, he rewrote Wolfenstein 3D to it. Unfortunately, when John Carmack left id Software, the code, the code is lost. And also, if you want to hear more about immutability, but in context of databases, I refer you to this presentation, Immutability Changes Everything. There, Pat Helland talks about immutability for an hour, so we won't do this today. And the next thing, coming right from the clean code book, is don't repeat yourself, which is, the phrase is repeated multiple times, the irony. And assuming you read the book, and you're concerned with separation of concerns, you've extracted all the bodies of your functions and conditions into new functions or methods or what suits you, then your code might look something like this. But there's again repetition in it. Higher order functions to the rescue. Higher order functions are functions which can accept other functions as parameters or can return new functions as the result. And for the first one, what does it do? Well, it applies some function on a data structure, creating a new one, transformed. And this operation is called mapping. And we have a map function. The examples are Java, Scala, and Haskell, which, well, what's the amount of mistakes that you can make when you have only the constructs on the right? You can't start with wrong element. You can't mess up the boundary. You will always increment by the round amount. So I would argue that the error space is reduced to 0. The next operation here is also very common. It's called filtering. You only pass to a new you are only interested in elements that pass a certain test given by the predicate you define. And the last one, this is folding or reducing, depending on the language you're in. Here you can still mess up with the starting element, 0 in this case, but you don't have to think about what each of those loops do, because on the left, there are 3 for loops, and there is something inside. On the right, the concept that the idea that the programmer wants to use is explicit. So the code is more concise. And again, there's a presentation, this time by Tim Sweeney. This is the guy that created the Unreal Engine at Epic Games. And in this presentation, he says that 90% of integer variables in Unreal exist only 2 index variables. And also, for loops in the engine, 30% of them are functional comprehensions, and next 50% are functional faults. And there were errors in those loops, which can be omitted if only there were a good tool at the time. The presentation is from 2005 to use higher order concepts during the creation of a really complex system, which is the game engine. So how do we create complex systems? Well, we divide it until it's no longer complex. So we build from simple stuff into less simple stuff until we have complex stuff. So this is an example. We've extracted 4 operations from our master method, but there's a problem with this code. I can switch action 2 and 3, and it will compile. Of course it will. But will it work the same way? Most probably not, because what's really behind it is that each action depended on the output of the previous action. This is also a thing from the clean code to expose the omnipresent hidden dependency of imperative code, which is time. When we have it written in this form, if all the parameters passed from one action to another are exposed, we can, very convenient example, only one input parameter, but we can do something like this at the top. This is not really readable, but it reassembles something that I saw in high school, mainly this. This was the operation, which is function composition. And by this, you can take 2 functions and create a new function from those 2. Is there something like this in Java and Scala? Of course, but it doesn't look really nice. That's probably why at least in the code I saw, it wasn't that popular method of composing programs, because it's not it's not simple. There's more noise. By comparison, if you ever read some Haskell code, you probably saw something like this, which is functional composition in Haskell. This dot operation is the small circle operation, which is function composition. But the problem with function composition showed like this is that we only can speak about pure functions. Pure functions are the ones that, well, don't have side effects. They expose all their input and all output in their declaration. So we have these pure functions. We have the function composition. It fulfills even some laws. It's associativity, commutative identity. By the way, the associativity of the composition operation is the reason why you are allowed to extract functions from your code. And you don't have to worry about anything while extracting pure functions. But this is more or less the type signature of this operation. You can't see the laser, but believe me. Because you read it from right to left, the parentheses in the middle are the first function, so A to B. The parentheses on the left are the second function from B to C. And what is the result of this operation? Well, it's a new function from A to C. Something more complex from two simple beings. But you want to create, well, useful programs. You need side effects. What can you do? Well, let's put on our mathematician's hats. We first think about representation. So MB, from functions from A to MB, from B to MC. What is M? Well, anything. It's file access, it's networking, it's databases, shared mutable state, it's concurrency, logging, error handling, output to console, to graphical output, anything you want to be. The only condition is when you want to combine multiple functions with side effects, the stack of the side effects must be the same for all the functions that you try to combine. Then what do we need? We can't use the dot, it's broken. So let's use a fish operator. Those are the fishes that swim from the right, just as the dot composes from the right. And you can do that as long as you fulfill the properties that were previously present for our pure composition. So you also need some identity operation. So now it's a pure, the function that we call pure in Haskell. And this is the type signature of the fish. It looks similar. The only difference is that now we can combine functions with side effects. But when I take off my mathematician hat, I don't want to read from right to the left. So here are the fishes that swim from the left. And here is the type signature. Only the parentheses, the contents of parentheses exchanged. The thing is, function composition, well, it's cool, but it's not as popular as function application. So with the fish operator, we also have the shove it operator. The shove it operator because we take a one value with side effect and shove it into a function that will accept a pure argument and produce new value with the same stack of side effects. Now, the fish operator is really called Kleisli arrow, and the shove it operator in Haskell is called bind. And of course, there is something like that in Java 8 and Scala. So we have flat map, and this is the proof. Those are straight from the documentation, and now with color. Sorry for the color blind, but you see that because in Java and Scala we're in the functional world, the left-hand side of the operator is hidden in the object that we try to invoke the method from. But the rest conforms. So if you ever used a structure that implemented this method, simplifying a bit, then you've already used a monad. So don't fear a monad. In Java 8, you only have, well, those two, but where the language lacks, the libraries provide. So you have functional Java, you have Java slang. Those two I didn't use, but I did use RxJava. And if you didn't, then believe me, if you do anything remotely associated with concurrency or asynchronously, then use RxJava. It will change your life forever and will make it easier. On the Scala side, we have well, better language support. For example, we have the try monad, which is the encapsulation of, which is built around the Java exceptions. And we have a future monad. There is a future in Java 8. It doesn't comply to the interface. You have the future monad, which well, eases your life when it comes to concurrency. But if this is not enough for you, then you have Scalas, which is well, it's an older library, still, but still maintained. And you have Cats, which is library built for newer Scala, but is not yet stable. At least that's what it says on the website. And there's also Eric Scala. By the way, the Eric's something are, well, there are at least 8 official versions for different languages that conform to the concepts. There is even Eric's CPP, although I haven't have opportunity to use it. Here are some clickable links that I intend to share with you. If you want to learn more about functional concepts and monads. Particularly interesting is Don't Fear the Monad by Brian Beckman, and also railway-oriented programming, because there a guy explains all the functional concepts without ever directly referring to them by name. So if you are still scared by a word on beginning with M, then won't be. There's a railway for you. And also the QuakeCon keynote, where John Carmack admits that the most bugs that they found in the engine for Quake this time were the parts that were not written in functional style. And the opposite was also true. So, and one more thing. All those concepts storm our current languages. They seem new and shiny, but they are not really. So this is the book written in first edition 1984. If you haven't read it, read it. It wasn't part of my curriculum on the university, but in the preface it says that it's for the it's an introductory course for computer science. And oh my God, there's everything. Well, mapping, filtering, yes, of course, but also the flat map is there. Lazy evaluation, continuation passing, even objects, but in a function. There's no object-oriented programming in there. There's also scheme in there, so beware, lots of parentheses. But it's really worth reading. I recommend you. It's available for free if you don't like paper for some reason. And well, my conclusion really is that functional thinking creates clean code. So use the concepts that are already in your language of choice, because you can write less and do more. Thank you.
Thank you very much. All right, guys, feel free to ask some questions.
Hey, thanks for the nice talk. We have a team that works with JavaScript, and there's quite some functional style stuff in there, maps, reduce, this filter. And also we use underscore and this kinds of libraries that add like a whole bunch more.
Yeah.
My question is, like, you generally work in the context of a team. The levels of understanding of functional programming are very different. We have some people that like to compose like a bazillion different like zips and filters and maps on their code, and then the question is, like, does the rest still understand it? Like, do you have any like good practices of like, should you push as much functional programming in there and just like have people understand it, or does it make sense to kind of like stick to the platform norms, let's say, right? If that makes sense.
Well, I would say coaching, code reviews, pair programming, they will work. That's what we use in my current team. There's different understanding of Scala, but we do all this stuff. So again, coaching, code reviews, pair programming, and we bring it up. Don't bring it to the lowest common denominator, because that won't bring you value.
Okay, so thank you very much
Thank you.
for your talk.